Thank you so much for joining us. My name is Katie Poser. I'm the Outreach Librarian for the NOAA Library, and we are very excited to be hosting today's seminar. Today's seminar is NOAA's Marine Carbon Dioxide Removal Engagement. So we are excited to talk about some emerging research on ocean climate solutions. Our speaker today is Gabby Kitch, who is the Ocean Acidification Program Marine Carbon Dioxide Removal Lead. So Gabby leads the marine carbon dioxide removal research and strategic efforts, which include managing the marine carbon dioxide removal research portfolio and developing new key partnerships to support the development research and products to enable the marine carbon dioxide removal ecosystem. And with that, I am going to turn it over to Gabby to start her presentation.
Thank you so much, Katie, and thank you to everybody for joining today, again, to learn about this emerging research topic within NOAA's overarching portfolio. As Katie said, I'm the Marine Carbon Dioxide Removal Lead with NOAA's Ocean Acidification Program. I'm really excited to talk to you over most of your lunch break, probably. So today we'll walk through a background on marine carbon dioxide removal, starting with what is carbon dioxide removal and why must we now consider it in our climate portfolio? And how does the ocean draw down carbon? For most of you, this might be an overview, but we'll start with the foundational knowledge here, and then we'll go into what is marine carbon dioxide removal. After we have that robust background on the scientific knowledge and state of the science, we'll move into what is NOAA's role and how NOAA is engaging. So to start off, I always like to start with this slide about the Intergovernmental Panel on Climate Change. In their most recent report, the AR6 report, they noted that in addition to now reducing carbon emissions, which is still the primary means towards meeting our climate goals, we must go one step further and remove carbon dioxide from the atmosphere in order to reach the Paris Agreement climate goals and targets. So this is a schematic put together from the World Resource Institution. This is a kind of a depiction of what the IPCC and others have shown in their robust scientific reports that has time on the x-axis and gigatons of carbon dioxide on the y-axis. So as we move through time, we can see this navy line on the graph as our climate goals to reach net zero and prevent warming above 1.5 degrees Celsius. And of course, current policies and our trajectory is not meeting this target. So as I stressed in the introduction of the slide, really steep emission reductions is our primary means to meet our climate targets, which is shown in the gray and blue shading above the 0 gigatons of carbon line. And these conventional mitigation techniques include moving to renewables, increasing efficiency, and also more innovative technologies like carbon capture, utilization and storage, where we are reducing the new emissions that make it into the atmosphere and putting that carbon elsewhere for utilization or storage. Now, the green shaded portion are those removal strategies. So this is removing legacy carbon dioxide that's in the atmosphere that was maybe emitted yesterday or 10 years ago through various approaches to do so. So this could include land-based approaches such as afforestation, so growing trees. It could also include more of those novel land-based technologies. Some of you might have heard of direct air capture, as our fellow federal agencies like the Department of Energy are really growing the resources sent towards those innovative and novel technologies. And it also includes the marine technologies or approaches that we will be talking about today here. And we know that the ocean is a really good option for carbon dioxide removal technologies. As we live on the blue planet, the ocean covers 70% of our planet. So it has a lot of space to be able to take in this carbon dioxide. And also, since the Industrial Revolution, the ocean has naturally absorbed 30% of carbon dioxide from the atmosphere. We'll go through how the ocean has done that in a moment here. So there's kind of two ways that the ocean can draw down carbon dioxide, and we're just talking again about the base state here, the natural ways that the ocean takes up carbon dioxide. And I will turn off my video so we can see the entire screen here, but I will pop back on at the end. So the ocean will naturally pull down carbon dioxide through two pathways. I'm going to talk about the inorganic, or kind of the non-biological way that the ocean draws down carbon dioxide here. So just as the air kind of interfaces with the ocean surface, CO2 is absorbed into the ocean. This CO2 is then converted into more stable molecules like bicarbonate ions. And once it's converted into those bicarbonate ions, it is what we call durably locked away. So this is an ion that can't easily exchange with the atmosphere anymore, only under certain conditions, which we'll talk about. And then the big thing to note here is that currently this exchange, or the absorption of CO2 into the ocean, is causing negative side effects such as ocean acidification. Ocean acidification processes here. I did include a note here that under certain conditions, CO2 can outgas from the ocean back into the atmosphere. This is largely dependent on temperature and other conditions. And the big point to call out here is, while the ocean has been providing, this natural way to draw down carbon dioxide from the atmosphere, moving forward into the future, it's unclear how much this CO2 kind of uptake will change with climate change and ocean warming. So to go through the ways that the ocean draws down carbon through biological processes, this is largely done by the biological pump. So this schematic here on this slide depicts a number of different pumps. I want you to think about the biological pump as all of these processes together. So this includes fixing carbon through the production of organic carbon. Just like on land, we have photosynthesis happening in the surface ocean. And then that organic carbon can settle into the deep sea, or perhaps onto the sea floor, or it can respire, just like on land with breakdown of organic matter on forest floors and things like that. Same thing can happen in the ocean. And that respired carbon may outgas back into the atmosphere, either on short timescales or longer timescales. To put these processes all together and the way that the natural carbon cycle looks, we can look at this graph, and I'll break it down a little bit for you. Similar to our starting slide, this has time on the x-axis, and it has what we're calling CO2 flux. So that's just gigatons of carbon dioxide per year on the y-axis. Note that the zero line is in the middle of the graph here. So we'll go over, what's above the zero line and what's below the zero line. Those things that are above the zero line are the sources of carbon dioxide to the atmosphere and to the Earth system. So we have fossil emissions, which make up a bulk of CO2 flux, especially in recent years. We also have land use changes, such as deforestation, just agricultural processes in general, those types of things for the sources of CO2 to the atmosphere. Below the zero line, we have the sinks. So we talked about the ocean acting as a natural carbon sink. Again, that causes things like ocean acidification. We also have the atmosphere serving as a quote unquote sink. As we all are familiar with, this growth of CO2 in the atmosphere causes warming to the planet. And we also have the land sink. So this is the green shaded area here, where the land, through processes like growing trees and just growing land biomass, will draw down carbon dioxide. So altogether, that is the natural global carbon cycle, where we have these sources and sinks. So really, when we're thinking about carbon dioxide removal, we're thinking about adding an artificial sink, if you will, or an additional sink, to be able to move that carbon dioxide out of the atmosphere and put it elsewhere into the Earth system. And to serve our climate needs, so again, to reach the Paris climate targets of limiting warming to 1.5 degrees Celsius, we need about 10 gigatons of carbon dioxide removal per year by 2050. and about 17 gigatons of carbon removal per year by 2100. So this is a massive undertaking in terms of drawing down carbon and creating this additional sink. If you look at this in terms of the natural carbon sinks, by 2050, we're going to have to draw down, this is we as in the global community, going to have to draw down carbon dioxide on the order of what is the natural ocean sink, right? And the ocean that covers 70% of our planet. By 2100, we're thinking about something that's about half of the current yearly emissions. If we think about the infrastructure that goes into, the way that we live our lives and the ways that we emit carbon today, such as all of the infrastructure for cars and for construction and electricity and all of those things, you can imagine the big undertaking that this creation of carbon dioxide removal will take. To put it in other terms, you'll see on the slide here, this means that we have to scale carbon dioxide removal 30 times its present capacity by 2030. And this number is often evolving as we understand kind of the scale, the scope, and the challenges that carbon dioxide removal presents. Now, if we think about the traditional carbon dioxide removal approaches, such as BECCS, which is bioenergy, carbon capture and storage, and forest management, so that's afforestation and reforestation. If we think about what it takes to sustainably scale those processes, on a year-to-year basis, these two technologies or approaches can remove about 2 to 5 gigatons per year. And this is sustainable in this sense means, we're not sacrificing a ton of space for agriculture, for needed development, for water usage, etc. So the ocean must be utilized in kind of a global CDR portfolio to meet these carbon dioxide removal goals. So I'll go into a little bit more technical detail to break down the types of marine carbon dioxide removal. I like to subdivide these into the inorganic or the non-biological and the biological pathways, just as we did when we were talking about the natural ways that the ocean can draw down carbon dioxide. So for non-biological pathways, we are considering approaches like ocean alkalinity enhancement, which will, this is the way that the climate has, or the Earth has cooled climate over geologic processes by the breaking down of minerals from rocks, and that produces what is known as alkalinity. It's a basic substrate that then moves through rivers and into the ocean system. That added alkalinity allows the ocean to draw down more carbon dioxide, because carbon dioxide is an acid. Alkalinity is a base, so we're just thinking about going back to our kind of high school chemistry or whenever you last took chemistry and thinking about those neutralization reactions, right? You probably do them every day in your kitchen. And this also has the ability to potentially act as ocean acidification mitigation, as depending on the methodology. And of course, this is an area of active research. So that's one of the non-biological pathways, ocean alkalinity enhancement. You'll often hear this called OAE for short. Everybody loves acronyms in this space. And then we also have electrochemical approaches. I'll go through this in a little bit more detail, but you'll often hear electrochemical approaches often referred to as direct ocean capture. These approaches are very much like direct air capture, if you're familiar with CDR at large, but this is happening in the ocean. So really using membranes to strip CO2 off of the ocean water, and then taking that CO2, putting it elsewhere, either through, again, storage, utilization, other processes, and then that allows these CO2 depleted waters to return back to the ocean and draw down more CO2. I'll also note that these electrochemical processes, either through membranes or by using electrical currents, can be coupled with ocean alkalinity enhancement. It can be a way to produce the base or the alkalinity that's used in ocean alkalinity enhancement. Okay, so moving on to the biological pathways now, we have, I've grouped them into two main pathways here. We have macroalgal cultivation or aquaculture, so just growing of seaweed and sinking that seaweed. So just like we talked about the biological pump, seaweed will fix carbon or draw down carbon when it's making its biomass. And then usually that seaweed is used for other purposes. However, marine CDR researchers are looking at what if we took that seaweed and actually transferred it to the deep ocean so that it can no longer interact with the atmosphere, and that organic matter can stay at the deep ocean or maybe be incorporated into sediments depending on the processes happening in the deep sea, in order to remove that carbon from the atmosphere. There's the last biological pathway, which is ocean fertilization, which includes adding limiting nutrients to places in the ocean to increase productivity of phytoplankton and accelerate the biological pump in that way. So again, more biomass being produced even through phytoplankton at the surface ocean, and that phytoplankton will settle to the deep sea and maybe eventually sediments. This I've also grouped, you'll see in the next slide, things like artificial upwelling and downwelling, which you might hear about, as that's largely moving nutrients through the ocean water column to enhance productivity. To give you a visualization of these different processes, we have those non-biological or inorganic processes on the left-hand side of this slide, and the biological processes on the right-hand side of the slide. So, of course, we have the ocean alkalinity enhancement. A couple of methods are shown here in terms of producing a base and then putting that base directly into the ocean or just offshore. Oftentimes, this is coupled with, or researchers are looking at coupling it with sewage outfall treatments and putting alkalinity into that sewage outfall. There's also, the actual mineral products. So things like olivine that are mafic rocks. Those are usually what contribute on geologic timescales to adding alkalinity to the Earth system. You can place that either, close to riverbeds or on the coast to enhance the weathering process of those minerals. I have direct air capture depicted here. You can see, again, once that CO2 is stripped off of the water, the carbon has to be stored somewhere. In this case, it is shown either being stored in the deep sea, so actually being injected into the seafloor, which is an area of active research. Again, all of these areas are, or transported onto shore and used in a different way. The biological methods, you see macroalgal cultivation or aquaculture, and the sinking of that biomass to the seafloor, and ocean fertilization. The inset here, which might be too small to see, shows that artificial upwelling and downwelling using infrastructure for artificial upwelling to pull water from the deep sea to the surface ocean, for artificial downwelling, pulling it from the surface ocean to the deep sea, again, to accelerate the biological pump. Great. So with that robust framework of all the technological approaches here, we can go into how NOAA is engaging in this space and why NOAA is engaging in this space. So as all of you are likely familiar with, NOAA is one of the leading federal agencies investigating all aspects of the Earth system. This includes interactions between the oceans, the atmosphere, and how the planet's energy balance, carbon cycle, and ecosystems are affected by carbon emissions and other greenhouse gases. Since marine CDR will purposefully impact the Earth system, we must understand how effective and how safe these pathways and approaches are. So for marine CDR in particular, there are three main reasons why NOAA's scientific expertise primes the agency to lead in this space. The first is that NOAA is a leader in the ocean carbon science. We support 50% of the carbon cycle observations across the globe. We have, state-of-the-art modeling capabilities that really feed into understanding the ocean carbon cycle. Of course, these are truly ocean-based methods, and the ocean is an open, complex system. The ocean requires large and various scales of monitoring and modeling, which NOAA has a lot of expertise in and is the leading federal agency in. Lastly, NOAA's science, service, and stewardship mission is unique and among our federal family, and is the strongest fit to lead in this space, especially that stewardship element, right? We want to balance all of the different ocean uses that happen in the ocean to be able to support livelihoods and ecosystems. So finding how to do these methods safely and conducting the research on the safety of these methods is very critical and a strong space where NOAA can lead. So in June of 2023, NOAA produced a carbon dioxide removal research strategy. If you haven't been able to take a look at that strategy, there is a QR code here included inset on the front cover of the CDR research strategy, and it's at the bottom left-hand corner. That QR code will take you to the webpage, the main webpage for the CDR strategy, which has a link to download not only the white paper, so that's the full report, but also a 2-page fact sheet that summarizes some key elements of the report. The report goes through 4 main areas. First, it goes through the federal motivation to engage in carbon dioxide removal research for NOAA. It also goes through the state of CDR science. You'll find that there are, we'll walk through some of that information today, but this is a quickly growing space, and some of that information is bound to change, hopefully with the exciting research NOAA is supporting that I'll talk about in a few slides. The third component of that research strategy is really how NOAA's assets will underpin the foundational science that's needed for the marine carbon dioxide removal space and the CDR space at large, which I'll walk through in a second here on this slide. And then the last part of that is NOAA's vision for CDR research at large, which I'll also show in a few slides here. So digging into what are NOAA's assets that really underpin the foundational science needed to support the CDR ecosystem, and how could those assets continue to grow to engage in this space? These are grouped into 4 main buckets here. So of course, as I mentioned, NOAA has strong observing assets or networks, both in the global and coastal regions, and has supported a lot of technological development for sensors for the ocean carbon system. NOAA also has has supported a lot of modeling and is thinking constantly about how these climate models intersect with the Earth system and different climate projections. When we think about marine carbon dioxide removal, we are currently supporting some work to integrate those approaches into these world-class modeling systems to think about how to answer questions about scaling and projections of carbon dioxide removal pathways. Of course, NOAA supports a lot of environmental impact work and assessments, thinking about the existing infrastructure that exists through the ocean acidification program and understanding carbonate chemistry dynamics on organisms. Those assets can be leveraged, and of course, the ocean acidification research can be leveraged to understand the safety of these kinds of methods. And so the environmental impacts works includes not only monitoring, but also modeling and laboratory research to really understand the safety of these different methods. Lastly, NOAA's decision support assets are critical in this space. So these include, but are not limited to, things like data management infrastructure, marine spatial planning to support permitting decisions and balance ocean uses, aquaculture research, and of course our collaborative and conservation research, largely supported through Sea Grant and other programs. So there's a more detailed version of this. I believe it's table 2 in our strategy. If you want to look into that, there's many of the examples that we talked through also listed explicitly on this slide. I also want to highlight that in order to truly understand the efficacy and safety of marine CDR, expanded research is necessary through all of these key asset areas in order to fully support the marine CDR ecosystem. Great. So I'm going to backtrack to section 2 of the strategy here, which really talks about the state of the science for carbon dioxide removal and goes through sections with each of those different methods that we talked about. What I wanted to highlight from that section is some material on evaluating carbon dioxide removal methods. So this plot contains a lot of layered information. We're going to walk through it step by step, But really what this plot fundamentally shows is the trade-offs and important decision points for a carbon dioxide removal strategy. So we have cost on the x-axis on this plot, and effectiveness, which is essentially the gigatons of CO2 removed per year on the y-axis. And you can see a whole suite of carbon dioxide removal approaches, some of which we didn't even go into, but you will see those ocean methods placed on this plot as well. Those 4 quadrants of the plot group these technologies into, their different cost and effectiveness ranges. The size of the dot corresponds to how long will carbon be removed from the Earth system with these approaches. The shading of the dot corresponds to how closely do NOAA's equities and assets align with that carbon dioxide removal technique. So an unshaded dot would be something that doesn't overlay with NOAA's assets as described in the strategy, and a filled in dot would be that there's a lot of overlap and a potential for high engagement with those strategies. So the key questions to evaluating CDR methods include, do they remove carbon from the atmosphere? There's a key need here for monitoring, reporting, and verification. You often hear this called MRV or MMRV if you want to add in a measurement to the start of that phrase. And this is what a lot of the projects that are focused around assessing efficacy are really drilling into, is the need for MRV and how to appropriately monitor, report, and verify the carbon drawdown from all of these different methods. In terms of cost, we're really thinking about things like infrastructure costs, like operation costs from energy. And we're also thinking about things like sustainability. So if the carbon needs to be stored somewhere, does it need additional infrastructure and additional costs to go into that storage capability? I will also note, not included in this plot are the kind of side effects, if you will, or potential ecosystem responses, community responses. So these are things like competing use cases, which we mentioned a few times, and also justice concerns for communities where these projects might be rolling out. So I do want to highlight that that information is not explicitly included on this plot. And the last point I'll leave you with here is take a look at the error bars that are associated with this plot. You can see that the error bars are quite large, both in terms of assessing cost and assessing effectiveness. And in some cases, this is because the cost and the effectiveness are very location dependent, regionally dependent, maybe even project dependent, but also largely because there is a need for more research into this field to assess both the effectiveness and the cost to be able to appropriately assess and narrow in on those values here. It's also worth noting that, as I mentioned, certain things were left off of that cost versus efficacy plot. A big one that was left off is the question about safety. And so safety really comes into play when looking at the ecosystem impacts. And marine carbon dioxide removal could have important implications for the marine environment. This plot here shows a qualitative way of looking at the potential effects of marine carbon dioxide removal on the ecosystem. This is also from the CDR research strategy, if you want to take a closer look at it. In the gray rows, we have the different methodologies that we walked through today. And then in the columns, we have all the potential impacts or responses of the marine environment to marine CDR. So I won't walk through all of them here, but it's worth noting that each method will have a potential impact, right? By nature, marine carbon dioxide removal means to have an impact on the environment. Some of these impacts may be, or responses, I should say, would be more of a potential negative, and then others could have a potential co-benefit or positive which we mentioned in terms of mitigation of ocean acidification. There could also be, increased productivity. This elevated pH alkalinity would directly affect, a positive to mitigating ocean acidification. Just like the error bar shown on the previous graph, even though we don't have error bars to show the implications for maybe more quantitative measurements on ecosystem impacts, it's worth highlighting that similarly, ecological measurements and ecosystem measurements are complex, and they can often take a lot of time. So there's often high natural variability in ecosystem response. There's mobile species. There's a lot of drivers. So how do we decouple the effects of climate change and the effects that marine carbon dioxide removal might have on an ecosystem if we're executing field research in a time of changing climate? And then there's also a lot of long time lags and a lot of different species. And of course, we mentioned the non-stationary nature of organisms, especially at the higher trophic level. So this is another complexity to layer on and a big research area in terms of evaluating the safety of marine CDR methods. Okay, so to walk you through what does the strategy say about carbon dioxide removal research at NOAA, and how does the strategy outline what this vision for NOAA research is? And I'd be remiss to say, before showing you this vision at NOAA, the CDR research strategy was a cross-line office. So in NOAA, those are all of the different kind of the different topical areas that NOAA focuses on, to put it most simply. So a cross-line office effort with many different primary authors, over 60 contributors, many different reviewers, both in terms of at NOAA and externally in other federal agencies. And so this really was meant to be a full NOAA vision for carbon dioxide removal research. With that background, I'll talk about what we are currently doing now. Really what we're calling Wave 1, which is the first step in this vision, is parallelized foundational research. So we're talking about conducting the laboratory studies. We're talking about growing carbon observations, developing the modeling packages, supporting development of permitting infrastructure, and especially the research needed to inform permitting decisions, and of course, early invested community engagement. In 2 to 5 years, we are thinking about, okay, how do we synthesize these research results? How do we do more process studies on ecosystem impacts, having, hopefully done a robust amount of research? How can we best utilize our existing assets to take part in large-scale demonstration projects? So thinking about field research and playing a role in terms of verifying the carbon and perhaps the safety of those methods in the field. How do we compare the different approaches in an analytical way? And then when we're thinking about Wave 3, this is really the mature global monitoring kind of wave. So this would be what happens if we were to have a project that is executing carbon removal on the gigaton scale. As is our ultimate goal with carbon dioxide removal at large. So with the gigaton scale, we're thinking about developing strong public-private partnerships that would really allow for NOAA to play this role in verifying the amount of carbon that's drawn down through observing and modeling. Okay, so I do want to back up on this slide really quickly. In terms of what's active now, we're going to go through the research portfolio in the next slide, so you'll be able to hear a little bit more about what external research we are supporting. But I do want to specifically note that we are growing our capabilities in those laboratory bench studies. We are currently integrating modeling capabilities and packages into larger Earth system models and regional models in some cases. And we have worked really closely with our federal partners in terms of permitting of these projects and understanding the existing gaps in the permitting or in the research that would inform permitting decisions. And we have just started to scope out some additional ways to really engage with invested communities in this space. So I would say in terms of what's active now, we're hitting on a lot of these different goals. The largest one that I would maybe highlight as underserved is the designing and growth of local and regional ocean carbon observations, which is, a critical NOAA mission line outside of marine CDR as well. Great. Okay, so to talk a little bit more about our research that we're supporting, NOAA's Marine Carbon Dioxide Research Portfolio is really led by the Ocean Acidification Program, but on behalf of the National Oceanographic Partnership Program, otherwise referred to as NOAA. The NOAA kind of umbrella is a vehicle to bring together multiple different agencies and also allows for private partners, so philanthropic money, to partner with a NOAA call. And the NOAA umbrella is really wonderful for the marine carbon dioxide removal space, as it was founded and mandated to support ocean science that crosses agency mission lines. And so this has been a really great mechanism to bring together the agencies and support these types of projects that really do cross agency mission lines. So in fiscal year 23, so these projects were awarded in September of last year, we supported 17 marine carbon dioxide removal projects to a tune of $24.3 million. This included an influx of $14 million from the Inflation Reduction Act. And at a high level, we supported, even though there were 17 projects, we supported nearly 50 institutions and 80 unique principal investigators. And I think that's a really great kind of statistic to hone in on, and that showcases the power of the NOAA. So not only does NOAA allow us to bring together the agencies that are shown on the slide here, critical partners in executing the funding, but NOAA also has an eligibility requirement to have multi-sector applicants to a call, which really is showcased by the reach of this program. So just to demonstrate the reach of this program, these are all of the partners that are listed on the slide. Again, these are the unique institutions, so the almost 50 of them. And, with additional kind of like hiring and shuffling of staff, I think this number has also increased as of late. Great. I'll go back to this slide one more time just to highlight a few additional projects that I do not have slides for, but I would be remiss not to highlight them here. So we did leverage the NOAA in FY22 as well, and we had a federal call through the NOAA, and we supported one project that is based out of the Cooperative Institute at the University of Washington at the Pacific Marine Environmental Laboratory. Also includes partners with the Pacific Northwest National Lab, PNNL, along with an industry partner. Again, this is a NOAA project, so multi-sector in nature, and that project has focused on ocean alkalinity enhancement and done a lot of really great work getting a ocean alkalinity enhancement system online at a national lab, and been doing a lot of research there. In the FY24 to 26 window, we're supporting, so that's the Ocean Acidification Program, is supporting some ecosystem response work at the Pacific Northwest Fisheries Science Center, looking at the effect of ocean alkalinity enhancement or just elevated pH and alkalinity in general on a number of different culturally and economically sensitive species to the Pacific Northwest area. Great. This QR code here that I didn't call out in my initial run through of the FY23 portfolio takes you to a landing page that has a news story on the funding opportunity. I also encourage you to scroll down. There's some discrete links to all of the different projects in this portfolio that our communications lead did a wonderful job of putting together. All of those are in largely plain language summaries as to why the work matters and what each project is doing. Okay, wonderful. So I wanted to focus in on what is next in terms of marine carbon dioxide removal. I highlighted a few different kind of interagency calls and efforts that we have really been participating in on the NOAA side. At large, with the Biden-Harris administration, carbon dioxide removal and looking at novel ways to meet our climate goals have appeared in many different executive orders and fact sheets and reports. And I'll call out that the Ocean Climate Action Plan, which was released in March of last year, was really key to highlighting the importance of marine carbon dioxide removal in meeting our kind of net neutral climate goals. Marine carbon dioxide removal is one of the priority kind of actions in that report. And if you look through the Ocean Climate Action Plan, you'll notice they tried to prescribe kind of agencies that would lead and support in this space. And NOAA shows up on the lead of 75% of those actions under marine carbon dioxide removal to highlight the agency's significance in this topic. So the Ocean Climate Action Plan was the impetus for this new Marine Carbon Dioxide Removal Fast Track Action Committee, which launched in October of last year. And the goal was to develop a research strategy on marine CDR that really hits on 3 different criteria. So thinking about clarifying permitting and regulatory roles, thinking about what is the critical research and development needs, and also public-private partnerships. NOAA is co-chairing the Fast Track Action Committee with the White House Office of Science, Technology, and Policy, so is playing a lead role in this manifestation of the OCAP into the Fast Track Action Committee. I've included yet another QR code here on this slide if you're interested in learning more about the Fast Track Action Committee. It's to the Federal Register notice, which has very much closed at this point. However, I think that it gives you a lot of really great background information on the Fast Track Action Committee. The research plan will be released this fall, so it's living up to its fast track name of producing a research strategy on a very quick timeline here, so keep your eyes out for that new strategy. I also want to note that there are many different agencies playing a role in this space, even though I highlighted NOAA's role. I believe there are over 14 different agencies that are participating in this conversation on marine CDR. Good. So the last thing I want to leave you with after you have, or I guess the second to last thing, is really to talk a bit about the permitting space for marine carbon dioxide removal, as it has been a little bit opaque in terms of what the pathways are and those types of things. I want to definitely say that I am not a regulator myself. I am on the research side. I support the research portfolio. So the information shared here has been cleared by our regulatory colleagues and is shared on behalf of them. So I'm not the best person to answer questions about this, but I can provide a high-level overview of the information so that to clarify maybe any questions that have been cropping up in the space. So there are 2 main permitting pathways to execute. We're talking about field research for marine carbon dioxide removal under the Marine Protection Research and Sanctuaries Act, or the MPRSA, under the US EPA. That would be projects happening in kind of federal waters or off the coast. And then there's also the Clean Water Act, Section 404, which issues these non-pollutant discharge elimination system permits, or NIPDES permits. Those are the ones, if you remember when I was talking about ocean alkalinity enhancement, those would be the ones utilized when ocean alkalinity enhancement is coupled with an outflow from a coastal system. So something like a sewage outflow, or even, a lot of laboratories have these for their mesocosm experiments, et cetera. If you're looking for more information specifically on MPRSA, you can visit the EPA's website, and you can also reach out to them. They always welcome inquiries and questions about permitting, especially if you're looking to do a project or ramping up for that. So reach out to this email here. The Army Corps of Engineers also has permitting authority under the Clean Water Act under Section 404 and the Rivers and Harbors Act. So this is really anything that is happening in the coastal system, on the beaches, in the rivers, etc., will largely be Army Corps kind of purview in terms of permitting. Of course, NOAA also has a lot of conservation and management marine resources equities in the space. And so I've listed a few of the different statutes here that would apply or might apply in the marine CDR space that are good to be aware of. So, of course, the Endangered Species Act, the Marine Mammal Protection Act, Magnuson-Stevens Act, Coastal Zone Management Act, which is usually implemented by states, but of course NOAA can play a role as well, and the National Marine Sanctuaries Act. So all of these listed on this slide here may contribute to the implementation as a consultant on marine resource management decisions, again, playing a role into making sure this research happens safely along with effectively. Okay. I'm going to zoom out for this last point here, talking about why does this matter outside of NOAA? How much of a reality is marine carbon dioxide removal going forward? And why is it important to engage in the science right now from an agency, right now coming from the agency? So thinking about just in terms of the different players in the space, we have folks from the private industry and also from the federal government who are acting as buyers of carbon dioxide removal credits and MCDR. We also have private kind of folks who are acting as registries. So those are where companies could go and actually buy these marine carbon dioxide removal credits or carbon credits more generally. Verifiers will ultimately be play a role in this space, but of course, right now we kind of see a merging of registries and verifiers happening in one place. And just to highlight again, if we, were to move forward with this gigaton scale removal manifestation of marine CDR, NOAA definitely envisions itself through the CDR research strategy as playing a role in verification and validation. And then lastly, we have the sellers. So there are many marine carbon dioxide removal companies in this space coming forward to sell the removals, specifically from a few techniques right now. We have direct ocean capture, or some people call that direct ocean removal, and ocean alkalinity enhancement. Companies have come forward also to sell on macroalgal cultivation and sinking, but have been recently phased out of this diagram itself. And this is all to stress that quality carbon credits through this private kind of landscape really relies on monitoring, reporting, and verification, that MRV, through observations and modeling. So we're at a really, really unique point in time right now where NOAA engaging in this space and producing, fundamental science has the ability to inform, what these market standards look like and what the landscape will look like to inform both the sellers and buyers of the space to make sure that carbon removal credits from marine CDR actually will have a climate benefit in addition to, really propping up this new emerging market. So with that, I think I'll turn it back to Katie for Q&A.
Awesome. Thank you so much, Gabby. We are going to move on to Q&A, and I'm going to bring Gabby up on the screen so we can bring in our questions. But the first question I have, and I promised I'd ask, is can folks access these slides?
Yes, Katie, I don't know what the best sharing method is, but I believe it is totally appropriate for these slides to be accessed. A lot of them come directly from that carbon dioxide removal strategy as well. So if you're eager to get your hands on some of the graphics shown, definitely check out that resource.
Awesome. I can have folks I can email our registrants with that link to the slides or a PDF copy, whichever you prefer, Gabby.
Sounds
Awesome.
great.
So our first question is going to be sent in by Bruce. Are we seeing any similar efforts across the international community?
Yeah, this is a great question, Bruce. And yes, we are seeing a number of international efforts crop up, a lot of efforts that are happening um, in the EU, specifically Germany. We are, connecting with those through the UN Decade on Ocean Science. So that's through an initiative called CDR-MAR at GeoMar and others. We also have seen the international community come together to produce best practices guide, largely for ocean alkalinity enhancement. There's other efforts cropping up. Australia is starting research efforts. A number of companies are starting to build up their pilot studies abroad. And another effort that I'll highlight is that some NGOs are supporting testing facilities both in Canada and in Iceland. So a lot of activity internationally as well to support the foundational research.
Thanks, Gabby. Our next question is many MCDR methods require carbon sequestration in the deep sea. Will ecosystem effects in the deep sea be explicitly evaluated?
I would say that absolutely. In the CDR research strategy and that kind of qualitative table, we call out a few of the effects for things that involve, bringing carbon down to the deep sea, and concerns there like increased ocean acidification from, respiration and remineralization of organic carbon, things like hypoxia, et cetera. Those are definitely, ecosystem responses that might have a negative impact, and I think they certainly qualify as foundational research questions. For example, one of the projects we're supporting in the NOAA portfolio is a modeling approach to look at, what are the effects on the benthic ecosystem from things like sinking biomass to the deep sea and also deep sea trawling. So thinking about how those ecosystems are impacted and how we can do that through a modeling approach.
Thank you. So, our next question is where can we find current information about MCDR companies that are selling removals?
Yeah, so I would say that there are a few resources out there, and I'll also preface this by saying this is not an endorsement of any kind of other resources that are out there, but rather just a bit of information sharing. So I would highlight maybe going to the different companies who are, buying or, facilitating the purchasing of different carbon removals or offsets. So one of the front runners that comes to mind is the Frontier and Stripe Climate and their initiative for an advanced market solution to purchase carbon credits, and they're definitely purchasing a few marine carbon dioxide removal kind of I guess the companies that are selling in that space are highlighted there. I wouldn't say that the general public has access to exactly all of the companies that are selling removals, but that might be a good starting point to look at, who is purchasing that. Microsoft is also a big purchaser, and then the Department of Energy will be purchasing carbon credits in the future, and they've announced their semifinalists for that purchasing pilot prize. So you can also visit their website to see who made it to the semifinalists there.
Thanks, Gabby. Next question is what role can NOAA play in supporting voluntary carbon markets?
Yeah, so I would say that this really comes back to that ending slide here. And so I'll answer it in the same way in the context that I provided in that last slide to not make a claim for all of NOAA. But I think, especially as a Department of Commerce agency, we can play a role in supporting the integrity of the voluntary carbon markets. Like I said, we're in a unique position for marine carbon dioxide in particular, carbon dioxide removal in particular, where the science is really emerging at the same time as the standards for both voluntary and the few compliance markets that exist. And so really making sure that as best as possible that NOAA can partner and facilitate kind of the creation of the standards that are truly informed by the best science and the emerging science, I think is the most critical role to make sure that we are facilitating the voluntary carbon markets and the integrity of those.
Thanks, Gabby. I'm going to grab another one from Nico here. So, how has NOAA's approach to community engagement evolved?
Yeah, I would say this is definitely an area that we would like a growth area for us. Of course, we would love to continue to leverage kind of the extension programs that NOAA has through Sea Grant and also the existing community engagement work that the Ocean Acidification program supports through, for example, the coastal acidification networks and those types of things who are increasingly more engaged in the marine carbon dioxide removal space. But we are currently working with some partners in the federal agency to better come up with specific key points on community engagement. And I would definitely plug the Fast Track Action Committee report that will come out this fall that talks a bit more about this specific topic.
Thanks, Gabby. We've got one from Skylar, focusing on how if the next 5 years are looking at results, demonstration, cost benefit, how are we achieving the 30 times increase?
It's a great question. And this is a fast moving space, right? We're up against the urgency of climate change and the climate crisis. So everything seems to be happening simultaneously. But I will say, the 30 times increase by 2030, right now, marine CDR is happening at a near zero gigatons of carbon removed. I would love to see an updated compilation of exactly, the exact research projects, how many gigatons of carbon. There's definitely not gigatons of carbon removed, but how much carbon is removed through all of those projects. So really accelerating the research in this space right now is, I think, a way to be able to facilitate, eventual decisions about scaling that will come down the line. So really, we're thinking about layering on research to get up to, a larger research scale by 2030. And, whether we reach that 30 times mark, I think it's too soon to say.
I'm going to squeeze in a last question in the last minute. Do activities like bottom fishing or dredging make MCDR less effective, or is this something that will be looked at in the future?
Yeah, so I think that if MCDR were to, let's say, scale, and there would be a lot of methods that are sinking a lot of biomass to the deep sea, then there could be a world where, yes, bottom fishing, dredging, so turning up the sediments on the deep sea would interact with the efficacy of those specific approaches and methods. I think at this point, we're trying to answer just like the foundational research questions. So what are the impacts of that biomass in the deep sea before getting to, how do these use cases come together in a more complex situation?
Thanks so much, Gabby. We are out of time. If we did not get to your question, we will be sending those on to Gabby to answer offline via email. Thank you, everyone, for joining us, sticking in through this amazing presentation on NOAA's Marine Carbon Dioxide Removal Program. And Gabby, any last words?
No, thank you all for tuning in, and feel free to reach out if you have additional questions or you would like to continue the discussion.
Thank you, everyone. Have a wonderful rest of your day.